I am going to share the screen. Okay, now I am going to share the screen. All of you will see that. Okay, share. Yeah, I hope all of you can see it. Okay, I hope you can see the screen. Okay, so as we are discussing in the last class, W reinforced beams means we will provide reinforcement both in the tension as well as in the compression side. Okay, so but we have to know under which conditions we will provide this W reinforced beam. Okay, so in the last class I told you, and again today I am repeating the same things, that if you go for single reinforced beam, then in some conditions, in some situations, due to the restriction of space or some architectural consideration also, you will see that the actual moment which is developing on the beam is more than the amount of bending moment which can be resisted by a single reinforced beams. So in that case, we will have two options. You can see here, either we can go for over reinforced section or we can use a W reinforced section. Okay, so but we know that over reinforced sections are not economical, and also it is very risky. Okay, so we have only one option left, that is we have to use W reinforced section. Okay, and here also it is, everything is mentioned here. The extra steel provided in the tension and compression zone constitutes the additional moment of resistance greater than RBD square. This RBD square amount of moment will be resisted by a single reinforced beam. That means if you provide reinforcement only in the tension side, it will resist this amount of bending moment. Okay, but in some cases the value of bending moment will be more than this RBD square. So in that case, the extra amount of, for resisting that extra amount of bending moment, we have to provide extra amount of steel, both in the tension side as well as in the compression side. Okay, so in this PDF you can see the necessity of W reinforced sections. These are the main conditions in which we will use W reinforced sections. The first one is the most important one. Wait, I will mark it. The first one is the most important one, as I have already told you that we have to remember one thing. Whenever the size of the beam is restricted, that means the size of the beam is fixed. We can't increase or decrease the size, and the available moment will be more than the amount of moment which will be resisted by single reinforced beams. In that case, we have to go for W reinforced sections. Okay, this is the okay. So wait. Now, okay. So now you can see we have to know how to analyze the W reinforced beams. So you can see first our aim will be to find out the modular ratio, and the formula is same with the single reinforced beams. First, in this W reinforced beam, we have reinforcement both in the tension side as well as in the compression side. So modular ratio for tensile steel will be same. You can see the formula which we have used so many times, M equal to 280 divided by 3 sigma CBC. Okay, so this is the modular ratio for tensile steel. Then we have to find out modular ratio for compressive steel also. It will be nothing but 1.5 times of this M. MC, C for compression, it will be 1.5 times of this value. Okay, so next, next here you have to see the area of the compression area consists of this part is the compression area. Okay, this is our compression part above the neutral axis. This portion is our compression part. Okay, so this part is called our compression zone or compression part, because above the neutral axis we all know that compression will develop above the neutral axis. Okay, so this part now will consist of two things. One is our concrete, and another thing is this stills which we are provided. This is a part of this compression zone. Okay, so we have to find out the area of the concrete as well as we have to find out the area of steel. Okay, so if we assume that the area of steel is ASC, area of steel in compression, A for area, S for steel, C for compression. Okay, and here you can see AST, A for area, S for steel, T for tension. Okay, so in the whole syllabus we will indicate AST for area of steel in tension side. That means whatever reinforcement we will provide in the bottom, for that steel, if you have to write down the area, we will write AST, that means area of steel in tension. And for the compression zone, whatever steel we will provide, we will write down the area of that steel will be ASC, area of steel in compression. Okay, so now you can see here the area of concrete above the neutral axis excluding the area of compressive steel equal to B into N minus ASC. B into N means this is our width B, this is our N, so total area will be Bn minus ASC, that will give us the area of concrete. Okay, here you can see here. Next, the area of compression steel ASC is replaced by an equivalent concrete area. So the concept is that we have to replace this area of steel by an equivalent amount of concrete. So for doing that we don't have anything to do, only we have to multiply this value by the modular ratio. Okay, you can see here the modular ratio of that steel is MC. So MC into ASC, that will convert the area of steel into equivalent amount of concrete. Okay, so now the total area of compression zone will be, you can see here, just add the two values Bn minus ASC plus MC ASC. This is the area of concrete, this is the area of steel. Okay, so you can see here everything is written here. You can see all the things. Okay, I hope you can understand. This is very simple. Just add the two values. You can take common ASC, you can take common MC minus 1. Okay, okay, so next you can see here the stress in equivalent concrete area. Okay, the stress in equivalent concrete area is sigma C dash, and the stress in compression steel is found as sigma SC equal to MC into sigma C dash. Sigma C dash is nothing but the stress at this level, at this steel level. Okay, so sigma C dash. So sigma C dash we can find out by the formula. We know that, again you can see here the stress in equivalent concrete. So whenever the equivalent word will come, then you have to know that we will multiply the value by modular ratio. Okay, so here you can see area of steel in concrete, stress in steel in compression, that means sigma SC equal to, this is the modular ratio for compression steel, and sigma C dash is the stress in that area. Okay, we know that MC equal to 1.5 times of M, and sigma C dash will remain same. So this is the formula to find out stress in compression steel. Okay, stress in compression steel, this is the formula. 1.5 times 1.5 into M into sigma C dash. Okay, so next our aim will be to find out the critical neutral axis. Critical neutral axis, the same formula we will use. You can see this formula we have used so many times. You can see it is written here. It is same as that for a single reinforced section. Then we will find out actual neutral axis. Okay, actual neutral axis is written by a small n. You can see the formula here. In singly reinforced beams, we have the formula Bn square by 2 equal to M AST D minus N. This was the formula for singly reinforced beam. Okay, so now you can see this portion came because now it is your doubly reinforced section. That means we have reinforcement both in the tension side as well as in the compression side. Okay, So you can see the formula. You can see here this formula bn square by 2 equal to m ast d minus n. This is the formula for single reinforced beam. This was the formula bn square by 2 equal to m ast d minus n. This was the formula for single reinforced beam. Now since it is a doubly reinforced section, we have to add one additional part, that is 1.5 times of m minus 1 into asc n minus d dash. Okay, this asc means area of steel in compression. D dash means it is the, what is that? D means effective depth. It is the C. You can see here. This is our D dash. It is the effective depth for compression steel, and this small d is known as effective depth for tensile steel. Okay, that is our D dash. Okay, so these things will be given to you. Okay, and if it is not given, then also we can assume that value. Okay, we can assume some value in some questions. But in most of the times, these values will be given. This D dash will be given. Okay, this D dash will be given to you. Okay, so now after getting the values of actual neutral axis and critical neutral axis, we can compare the values. Okay, if n is less than nc, then it will be, what will be the value? If n is less than nc, what will be the type of section? If depth of actual neutral axis will be less than critical neutral axis, then what will be the value? What will be the type of section? If depth of, can you go please lower? Okay. Yeah, under reinforced. Yes, good. If depth of actual neutral axis will be less than the critical neutral axis, then the section will be under reinforced. Okay, and if it is opposite, that means if the depth of actual neutral axis will be more than critical neutral axis, then the section will be known as over reinforced section. Okay, so now you can see here the stresses in the section. Now it will be little bit different. Maximum compressive steel in concrete, maximum compressive stress in concrete, as we have already know these things, it is sigma CBC. That means it is the maximum amount of stress that will be developed in concrete, and it will develop at the topmost layer. Okay, that is written by sigma CBC, and this value we can calculate from table number 21. Okay, then you can see here the stress in equivalent concrete at the level of compression steel. Okay, it will be written by sigma C dash. I have already told you sigma C dash. Okay, next, stress in equivalent concrete at the level of steel. Okay, at the level of tensile steel. Okay, this steel is not correct. This word is mistakenly printed. Okay, this at the level of tensile steel. At the level of, it should be at the level of tensile steel only. Okay, so it will be sigma ST by M. Okay, next, stress in compression steel equal to this much, as I have already shown you here. This is the thing. Sigma SC equal to 1.5 times of M sigma C dash. This is the thing. Okay, then stress in tensile steel equal to sigma ST. Okay, so now the moment of resistance, you can see here the moment of resistance of a doubly reinforced beam is written as MR equal to M1 plus M2. Okay, so what is this M1? M1 is the amount of bending moment that will be, you can see here, M1 is the moment of resistance of a similar balanced section without compression steel, or indirectly you can say that M1 is the amount of steel, amount of bending moment that will be resisted by a single reinforced beam. Okay, and this is the additional amount of moment for which we have to provide reinforcement. Okay, okay, this M2 is the additional amount of moment which is developing in that section, because of which you are providing extra reinforcement. Okay, this is the M2. So M1 we can find out same formula, M1 equal to C1 into A. C1 is the moment of resistance, your total compressive force, into A. A means your lever arm, which we have discussed in the first or second class. Okay, this was the formula we have used so many times in the single reinforced section. M1 RBD square. You can see here the formula half sigma CBC B into N D minus N by 3, or you can say it is RBD square M1. Okay, and M2 equal to C2 into D minus D dash. Okay, D is the effective depth for tensile steel, and D dash is the effective stress for effective depth for compression steel. Okay, so now you have to see what is this C2. Okay, you can see here where C2 is the compressive force carried by compressive steel. Okay, C2 is the compressive force which will be carried by our compression steel. Okay, so it can be calculated by this formula: C2 equal to MC minus 1 into AC into sigma C dash. You can see here equivalent area in terms of concrete into compressive stress, because we know that force equal to area into stress. Okay, force equal to area into stress. So area formula is MC minus 1 into ASC. Compressive stress at that level, at this level, will be sigma C dash. So if you multiply the two values, then you will get the value of compressive force. Okay, so our final equation for moment of resistance will be this plus this. This is our M1, this is our M2. Okay, you can see here the final formula of moment of resistance equal to half sigma CBC Bn d minus n by 3. This is our M1. M2 is this one. Okay, M2 is this one. Okay, so now in this expression, this sigma C dash we can calculate. Sigma C dash we can calculate from the stress diagram. Okay, as I have already told you so many times before, you have to, for if we have to if you want this subject to become easy for you, you have to know some things from mathematics. You have to know how to use the properties of similar triangles. Okay, okay, and you have to know how to find out the solutions for a quadratic equation, or if you have a cubic equation, then also you have to know how to find out the roots. Okay, then only you will find this subject is very easy. Otherwise you can use the procedure, but while solving the numericals, if you don't know how to put the values in those equations, in quadratic equation or cubic equation, in that case what will happen, you can't find out the roots, and in that case you won't get the full marks. Okay, so this subject is 60% mathematics, 40% is your concept. Okay, 40% you have to understand, and 60% is complete mathematics. Okay, and it is not that you have to know very detailed about mathematics. Only small formulas you have to know. How to solve those formulas you have to know. Okay, and most importantly you have to know how to use your calculator, because you have, all of you have a scientific calculator with you. So it will be very easy for you to learn how to use your own calculator. Okay, so that it will give you the answer of any problem within 2 to 3 minutes. Okay, okay, so now you have got the equation for moment of resistance for a doubly reinforced beam. Okay, so this is our final equation for moment of resistance. Okay, okay, so now we have to our in the entire equation, you can see everything you can calculate. Sigma CBC you can calculate from I square. B will be given to you, and you can find out by that formula. D will be given to you. M you can find out by using the formula. ASC you can find out. Okay, only the different thing is this sigma C dash, the stress in compression steel level. Okay, so but it is very easy to find out the sigma C dash by using the properties of similar triangle. Okay, so now you can see this is our stress diagram. You can see here this is our stress diagram. Okay, so in the stress diagram, you can see this one triangle. You have two triangles, this one, this big triangle. One is this is one triangle. Okay, and this is another triangle. This small triangle is another triangle. Okay, this is one triangle, and this big one is another triangle, and these two triangles are similar. Okay, so if you want to use the property of similar triangle, then what we have to do, if you take n of this big triangle, sir can't see the triangle, why? You can see two triangles are here. Okay, so can you see this? This is a big triangle, this one, this is one triangle. And this one another triangle, this small one, this area, this is another triangle. Okay, so these two triangles are similar. Screen is not the screen is visible. I hope all of you can see my screen. Hello, can you see the screen, all of you? Yes, okay, I hope you can see the screen. Hello, okay, so now okay, so now, okay, so these two triangles are similar. This one is your big triangle, this one is a small triangle. So if you take this length from this big triangle, which is our sigma CBC, we have to take this length from this small triangle. Okay, so our equation will be sigma CBC from this big triangle divided by this length. This is our sigma C dash. Sigma CBC divided by sigma C dash equal to this whole length. This is our n, equal to n divided by this length will be n minus d dash. That will be our equation. Okay, okay, so our equation will be sigma CBC divided by sigma C dash equal to n divided by this length will be n minus d dash. From that equation we can find out the value of sigma C dash. Okay, you can see here, actual equation was sigma CBC divided by sigma C dash equal to n divided by n minus d dash. From this equation we can find out the value of sigma C dash. Okay, here it is written from similar triangles. Okay, so now you can see these three types of problems. These three type of problem from doubly reinforced beam. Okay, it is same with the single reinforced beam, only the difference will be to use the equations. Okay, you can see determination of moment of resistance of the given section, as we have discussed in single reinforced beam also. In the first kind of problems only you will be asked to find out moment of resistance. In the second type of problem you have to find out the actual stresses, and in the third type, which is the most important one, design the section. Okay, design the section. So determination of, first we will discuss determination of moment of resistance of a given section. Okay, I told you the procedure before also. In this kind of problem, the dimension of the beam will be given to you. That means B will be given, D will be given, area of steel, AST, ASC, everything will be given. Permissible stress in concrete, sigma CBC, and permissible stress in steel, sigma ST will be given to you. These things will be given to you. So based on these values, first we have to calculate M by this formula. Then MC will be 1.5 times of N. Then we will calculate critical neutral axis by this formula, same formula with the single reinforced beam. Next, we have to calculate actual neutral axis depth by this formula. Okay. Then we have to compare the two values NC and N. Okay. Critical neutral axis, and this should be N. Okay. Okay. This should not be NC. This should be N. Okay. So we have to compare these two values. If N is less than NC, then we can say that it is under reinforced. This is wrong. This equation is also wrong here. It should be N less than NC. Then the section is under reinforced. Then maximum tensile stress in steel will be sigma ST, and the maximum compressive stress developed in concrete is this much. Okay. Okay, so in under reinforced section, only one thing will be different: the value of sigma c dash. This sigma c dash formula you can see here. Sigma c dash equal to sigma dash cbc divided by n minus d dash. And in this equation, this n will be known. Okay, d dash will be known. The unknown will be sigma dash cbc, and sigma dash cbc you can find out from this formula. Okay. So first you have to find out sigma dash CBC, then you put the value here, you will get the value of sigma C dash. Then this is the main formula for moment of resistance. Okay, so in doubly reinforced beam we have only one formula for moment of resistance. Okay, it is, but in singly reinforced beam we have two formulas for moment of resistance. For under reinforced section it was different, for over reinforced section it was completely different. But in doubly reinforced section we have only one equation for moment of resistance. Okay, but the difference will be to calculate the value of sigma c dash in both the cases. In under reinforced section the value of sigma dash cbc formula will be different. Okay, in under reinforced section the sigma c dash value will be this one, formula is this one. But in over reinforced section the sigma c dash value you can see here, the value will be different. You can compare the two equations. What is the difference? You can see this is the equation for compression steel, stress in compression steel for under reinforced section, and this is for over reinforced. Okay, so the difference you can see almost all the terms are same, only you can see it is written here sigma cbc and it is written here sigma dash cbc. Okay, so sigma cbc means it is the maximum stress which will be developed in concrete, and you will get the value from IS 456 from table number 21. But this sigma dash CBC is not the maximum permissible stress, and this value you can find out from this formula. That is the only difference. Okay, after getting the value of sigma dash CBC, you have to use the same equation. You can see here both the equations are same equations we have to use both for under reinforced as well as for over reinforced. Okay, next we have to, in the next type of problem we have to find out the stress in steel and concrete. Okay. Okay, when we will solve the numericals, then it will be clear to you. And the last one is the most important, the design of section. That means we have to find out the width of the, okay, that means we have to find out this thing, say determination, everything we have to design, everything we have to design, and which is the most important for doubly reinforced section. Okay. Okay, so let us start solving numericals, then it will be very clear to you. Okay, so if you have, okay, so I hope all of you have IS 456 with you, is it? Do you have IS 456 with you at present, all of you? Okay, so now I will show you this value. All of you must remember this value because this is very important in solving numericals as well as for competitive exam for any viva. Okay, maximum compression reinforcement, you can see the maximum compression reinforcement in a beam cannot be more than 0.04 times of B into D. That means 4% of the gross cross-section area. That means the maximum compression reinforcement, whatever reinforcement you are providing in the compression zone, the total area of the steel cannot be more than 4% of the gross cross-section area. Okay, gross cross-section area means the total area of the beam. Okay, B into D, this value B into D, 0.04 means 4%, B into D means total gross cross-section area. B means the width of the beam, capital D means total depth of the beam. Okay, so B into D will be the total cross-section area, and the maximum area of the steel, the area of compression reinforcement cannot be more than 0.04 times of BD. Okay, so now you go to IS 456. Go to IS 456. Okay, you go to clause number 23. Clause number 23 from IS 456. It might be in the page number 36, but I don't know exactly. You go to clause number 23. Go to clause number 23 point. Question numbers. Okay, all of you go to clause number this one. 26 point. It will be how much? Clause number? Yeah, 26.5. Go to 26.5. Clause number 26.5. It might be in page number 46. You can check that. Go to clause number 26.5. Did you get the clause, everyone? Go to clause number 26.5. Go to clause number 26.5. Did you get that? Did you get the clause? Okay. I hope all of you could find it. Okay, so 26.5. You can see here in the IS code, it is written that requirements of reinforcement for structural members. So if we are discussing about beams, then you can see the tension reinforcement. That means tension reinforcement means the steel which we are providing in the tension zone. That means at the bottom, below the neutral axis, whatever reinforcement we are providing below the neutral axis, that is known as tension reinforcement. Okay, you can see here the minimum amount of reinforcement, how much you can provide. We have to find out by this formula. This is the AS, means area of steel, and this is the minimum amount of reinforcement. You can see here minimum area of tension reinforcement. You can see here the minimum area of tension reinforcement shall not be less than given by the following. This is the formula, and in this formula, this AS, area of steel, this is the minimum amount of steel which we have to provide in the tension zone for any beam. Okay, you have to remember minimum reinforcement, this formula. AS will be how much? 0.85 into BD divided by FY. Okay, and this B into D, beam is your width of the beam, and small d is not the total depth, it is the effective depth. Okay, so this small b into d, this factor is actually known as effective area. Okay, effective area. So minimum amount of tension steel will be 0.85 times of effective area divided by Fy, yield stress. Okay, this is the minimum amount of reinforcement. And you can see here maximum amount of reinforcement. How much you have to provide maximum? The maximum area of tension reinforcement shall not exceed 0.04 times of BD. This you can mark it also. For any viva, if you are appearing a viva for structural analysis, this is the one of the most common questions they will ask. What is the maximum amount of tension reinforcement you can provide? Maximum area of steel in tension. How much it will be? 0.04 times of BD. Or you can say that it is 4% of the gross cross-section area. That means the total area of steel in tension zone cannot be more than 4% of BD. Cannot be more than 4% of total cross-section area. Okay. So next you can see here compression reinforcement. Compression reinforcement means the steel which we are providing in the compression zone. That means above the neutral axis. Okay. So for this also you can see the same thing is there. The maximum area of compression reinforcement shall not exceed 0.4 times of BD. Okay. So similarly in the compression zone also you cannot provide more than 4% of gross cross section area. Okay. These two values always you have to remember. Okay, for solving numericals also it is important. For appearing any viva it is important. For appearing any competitive exam this is very important. Okay. Okay, so let us start the solving numericals. Here it is written. Okay. So now okay, you can see the problem. You can see the problem here. All of you please go through the problem and see how they have solved it. Okay, all of you please read the question. The dimension of the beam is given 400 into 600. It is reinforced with 4 numbers of 25 millimeter dia bars in. Please read the question and see the solution and try to understand. If you don't understand, then you tell me, or then I will explain. Otherwise, same things we have solved so many times. I hope you have understood this part. Everything is very simple here. I hope up to critical neutral axis, all of you can find out. Is it? See, you can. It is very simple. Okay, so we have got critical neutral axis value is 173.87. Okay, so this is, I am not going to explain again this equation because we have used this equation so many times. Okay, so after getting the critical neutral axis depth, next we have to find out actual neutral axis depth. This is the formula. Okay, and all of you please try to solve this. Okay, all of you please take your pen and paper, write down these things so it will be easy for you to understand. Okay, so our first class will be over within 5 minutes. Then after that you can join the second class with the same link. Okay, with the same link you can join again for the next class. Okay, so now for calculating the actual neutral axis depth we have to use this equation. See this equation, bn square by 2 equal to this equation. So almost all values are given except this n. M is known, ASC is known, n we have to find out, d dash is given. Everything is given, only we have to find out n. So n we can find out by using calculator. Okay, n we can find out. So n value we have got, depth of actual neutral axis is 189.46 and critical neutral axis is 173. Okay, since n is less than critical neutral axis, then we can say that this equation they have written wrongly. Okay, yeah, depth of actual neutral axis is more than critical neutral axis, therefore The section is over reinforced. Okay. Therefore, sigma CBC equal, you can see the equation. Try to understand. If you have any doubt, you can ask me.